Einstein once imagined something so strange, so revolutionary, that even he doubted we'd ever see it ripples in the very fabric of space and time. 100 years before scientists finally caught their faint echo, his theory of relativity whispered about these cosmic tremors, gravitational waves, born from the most violent events in the universe. Picture space-time as a vast, invisible ocean, and somewhere out there, two black holes collide, a splash so powerful it sends waves racing across the cosmos at the speed of light. These aren't just scientific curiosities. They're the universe's way of telling its story, and for the first time in history, we're listening. Think about what that means. For millennia, we've relied on light telescopes capturing stars and galaxies to understand the cosmos, but gravitational waves, they're something entirely new. It's like being deaf your whole life and suddenly hearing the symphony of the universe for the first time. These waves carry secrets light could never reveal, the final moments of colliding neutron stars, the birth cries of black holes, even echoes from the dawn of time itself. And the most astonishing part, we've only just begun to decode them. That's where this journey begins. Over the next 24 revelations, we'll dive into the mind-bending science of gravitational wave astronomy, how these ripples are detected, what they've already taught us, and the mysteries they're poised to unravel. From the engineering marvels of detectors buried deep underground to the cosmic cataclysms that shake the fabric of reality, you're about to witness a revolution in how we see the universe. By the time we're done, you'll understand why this isn't just science, it's a new chapter in humanity's quest to understand our place in the cosmos. So let's step into the ripple. The universe is speaking. Are you ready to listen? On September 14, 2015, a ripple from the distant universe reached Earth, so faint it stretched and squeezed our planet by less than 1/10,000th the width of a proton. Yet that microscopic wobble, captured by the Laser Interferometer Gravitational Wave Observatory, or LIGO, shook the foundations of science. For the first time, humanity had direct evidence of two black holes, each roughly 30 times the mass of our Sun, spiraling into each other over 1 billion years ago. The signal, labeled GW150914, lasted just 0.2 of a second, a cosmic chirp that echoed across space-time. What made this discovery so extraordinary wasn't just the detection itself, but what it revealed. Einstein's equations had predicted such collisions would unleash gravitational waves, but even he doubted we'd ever sense them. The energy released in that final collision was staggering. For a brief moment, it outshone every star in the observable universe combined. Yet by the time those ripples reached us, they were quieter than a whisper. To catch them, LIGO twin detectors, separated by nearly 2,000 miles, had to measure changes in distance smaller than the nucleus of an atom. It's like trying to detect a single grain of sand added to the weight of the entire planet. The implications were immediate and profound. This wasn't just about confirming a century-old theory. It was proof that the universe speaks in more than light. Those black holes left no glowing debris, no visible trace. Without gravitational waves, their collision would have remained invisible forever. Instead, we heard it. That chirp was the soundtrack of space-time itself flexing, a direct line to the universe's most violent events. Within months, the discovery earned a Nobel Prize, not just for verifying Einstein, but for handing humanity an entirely new sense. Now the floodgates are open. Since that first detection, LIGO and its European counterpart, Virgo, have spotted dozens more mergers, black holes of all sizes, neutron stars colliding in bursts of gold and platinum, even mysteries we're still untangling. Each ripple is a puzzle piece, reshaping how we understand gravity, matter, and the cosmos itself. And this is just the beginning. With every new detection, we're tuning our ears to the universe's faintest whispers, learning to listen in ways we once thought impossible. To catch a whisper from the edge of the universe, you need a machine so precise it borders on the impossible. At the heart of gravitational wave detection lies an astonishing feat of engineering laser beams racing down tunnels longer than 3,000 football fields, bouncing between mirrors suspended so delicately they float like feathers in a vacuum. Here's how it works. When a gravitational wave passes through Earth, it warps space itself, stretching one arm of the detector while squeezing the other. The lasers inside sense this distortion, a shift so tiny it's like measuring the width of a human hair on the moon. But here's the real magic. LIGO and Virgo don't just detect these changes, they filter out a symphony of earthly noise. Every passing truck, distant earthquake, even the rumble of ocean waves could drown out the faint cosmic signal. That's why the mirrors hang from silica fibers thinner than spider silk, isolated from vibrations. The detectors also use a clever trick called active noise cancellation, similar to headphones that mute background chatter, but for space-time itself. By comparing signals from multiple locations, like tuning out static, by listening with both ears, scientists separate cosmic whispers from terrestrial interference. Why go to such extremes? Because what these machines hear rewrites astronomy. Traditional telescopes rely on light, but black hole collisions emit none. Gravitational waves slip through cosmic dust, carrying stories from places light cannot reach. It's the difference between watching a silent movie and suddenly hearing the characters speak. Each detection unveils hidden chapters: neutron stars spinning into oblivion, black holes dancing in the dark, perhaps even echoes from the Big Bang. And with every upgrade, these detectors grow more sensitive, tuning into frequencies we once thought were science fiction. The universe is full of secrets. Now we're finally learning how to listen. Black hole mergers are the ultimate cosmic heavyweight fights, collisions so powerful they momentarily outshine entire galaxies. When two of these invisible giants spiral toward each other, they don't just crash, they distort the fabric of space-time itself, sending gravitational shockwaves rippling across the universe at light speed. Take the record-breaking event in 2019, where two black holes, one 66 times the mass of our Sun, the other 85, smashed together in a cataclysm so violent it released more energy than all the stars in the observable universe combined. For a fraction of a second, space itself rang like a bell. What's truly baffling is how these monsters form. Conventional wisdom suggested black holes from dying stars couldn't grow much larger than 40 solar masses. Yet here they were, behemoths defying the rules. One theory points to the early universe, where dense clusters of massive stars might have collapsed directly into black holes without the usual supernova fireworks. Another tantalizing idea: these giants could be the products of previous mergers, black holes that grew by devouring others, like cosmic Russian nesting dolls. Each collision leaves behind a heavier remnant, setting the stage for an even more colossal showdown. But the real magic lies in what these mergers reveal about gravity's extremes. As black holes orbit each other, their gravitational pull distorts space-time so severely that time itself slows down near them. In their final moments before merging, they can reach speeds close to half the speed of light, creating a warp so intense it's like watching two whirlpools spinning into one. The resulting gravitational waves carry fingerprints of this chaos, clues about the black hole's masses, spins, and even the shape of space-time around them. It's as if the universe handed us a key to decode its most hidden laws. And then there are the exceptions, the rare, glittering collisions that don't just ripple silently through the dark. When neutron stars merge, they don't only send out gravitational waves, they explode in kilonovas, forging heavy elements like gold and platinum in their wake. Imagine, a single neutron star collision can produce enough gold to outweigh our entire planet. These events are the universe's alchemists, transforming raw gravity into the very elements that make up our jewelry and electronics. It's a dazzling reminder that the cosmos isn't just violent, it's also strangely, beautifully creative. With every new detection, we're rewriting the rulebook. Some mergers hint at black holes spinning in opposite directions. Others suggest mysterious middleweight objects that shouldn't exist. Each signal is a puzzle, a cosmic breadcrumb leading us deeper into the unknown. And as detectors grow more sensitive, who knows what other giants or ghosts we'll find lurking in the dark? On August 17, 2017, the universe handed scientists a gift wrapped in fire and gravitational waves. For the first time, detectors at LIGO and Virgo caught the spiraling dance of two neutron stars, city-sized remnants of dead stars, each so dense a teaspoon of their material would weigh 1 billion tons. But this wasn't just another cosmic collision. Telescopes around the world simultaneously saw the flash, a brilliant kilonova explosion painting the sky in radioactive gold. The event, catalogued as GW170817, didn't just confirm Einstein's prediction that gravitational waves move at light speed. It revealed something far more precious, the origin of the heaviest elements in our universe. Picture this violent alchemy. As the neutron stars merged, their crushing gravity ripped them apart, ejecting material at nearly 1/3 the speed of light. In the searing heat of this expanding cloud, atomic nuclei captured free neutrons faster than they could decay, forging gold, platinum, and other rare elements in a process called rapid neutron capture. Calculations suggest a single merger like this can produce hundreds of Earth masses worth of gold, scattering these cosmic treasures across galaxies. That ring on your finger, its atoms might have been born in a cataclysm older than our solar system. What made this detection truly groundbreaking was the dawn of multi-messenger astronomy. By combining gravitational waves with traditional telescope observations, scientists could study the same event through two completely different cosmic senses, like watching fireworks while also feeling their shockwave. The gravitational signals revealed the neutron stars' masses and orbital details, while the light show exposed their chemical fingerprints and explosive aftermath. Together, they painted a complete picture no single instrument could achieve alone. But the surprises didn't stop there. The kilonova's brightness defied expectations, hinting that neutron star collisions might also create mysterious intermediate mass black holes or even exotic states of matter. Some theories suggest quark-gluon plasma, a primordial soup from the universe's first microseconds, might briefly reappear in these collisions. Every new observation peels back another layer, showing these events aren't just cosmic gold factories but laboratories for physics we can't recreate on Earth. Now imagine extending this technique further back in time. If gravitational waves from neutron star mergers reach us after traveling billions of years, could they also carry echoes from the universe's infancy? Some models suggest waves from the Big Bang itself might still ripple through the cosmos, faint whispers of creation waiting to be heard. Future detectors could tune into these primordial frequencies, offering a glimpse of reality's first moments before the first stars, before the first light, when the universe was just a seething sea of space-time itself. Buried within the faintest gravitational waves could be echoes from the very first trillionth of a second after the Big Bang, a time when the entire universe was smaller than an atom, hotter than the core of a star and expanding faster than the speed of light. This cosmic inflation, a theory first proposed in the 1980s, suggests that quantum fluctuations in the infant universe were stretched to astronomical scales, seeding the galaxies we see today. But here's the mind-bending part. Those same quantum jitters might have also left behind a faint gravitational wave background, ripples frozen in time like fingerprints on space-time itself. Detecting these primordial waves would be like listening to the universe's first heartbeat. Unlike the sharp chirps of black hole mergers, these signals would be a whisper-thin hum, a static woven into the fabric of reality. To catch them, scientists are turning to space itself. Enter LISA, the Laser Interferometer Space Antenna, a trio of spacecraft set to launch in the 2030s. Flying in a perfect triangle nearly 2.5 million kilometers apart, they'll use lasers to measure distortions 100 times smaller than anything detectable on Earth, far from the noise of earthquakes, traffic, or even ocean tides. Why go to such lengths? Because these waves could rewrite physics. If detected, they might confirm inflation, revealing how the universe grew from subatomic to cosmic in less time than it takes light to cross a proton. But the real shocker, they could expose cracks in Einstein's theory of gravity. Some models predict these waves might carry hints of extra dimensions, hidden layers of reality curled up so tightly we've never seen them. Others suggest quantum gravity effects, where space-time itself behaves like a frothing sea at the smallest scales. It's like discovering the universe has been humming a secret tune all along, one that holds clues to everything from dark energy to the nature of time. And then there's the background hum, a symphony of overlapping gravitational waves from countless black hole mergers across cosmic history, blending into a steady drone. Like hearing rain on a roof instead of individual drops, this chorus could map the universe's hidden structure. Somewhere in that noise might lurk even stranger signals, cosmic strings, hypothetical defects in space-time left over from the Big Bang, or vibrations from colliding universes in a multiverse. The hunt isn't just about the past, it's about decoding the universe's deepest layers, one ripple at a time. Hidden beneath the chaos of individual black hole collisions lies something far more subtle, a cosmic murmur so faint it blends into the fabric of space-time itself. Scientists call it the gravitational wave background, the accumulated whisper of every merger that's ever shaken the universe. Picture standing in a crowded stadium. You might hear individual cheers nearby, but beneath them all, there's a constant hum of thousands of voices blending together. That's what astronomers are hunting, the collective echo of millions of black holes dancing in the dark over billions of years. To catch this whisper, researchers aren't using LIGO laser tunnels, but something far older, the universe's natural timekeepers. Pulsars, spinning neutron stars that flash like cosmic lighthouses with atomic clock precision, act as a galactic scale detector. When a gravitational wave passes between Earth and a pulsar, it subtly alters the timing of those flashes, stretching or compressing space like a funhouse mirror. By monitoring dozens of these pulsars across the Milky Way for years, scientists can spot patterns, tiny delays or advances that betray the background hum. It's like listening for the faintest rhythm in a symphony of static. The payoff: this hum could reveal supermassive black hole binaries, pairs of monsters weighing billions of suns, lurking at the hearts of merging galaxies. Unlike stellar mass black holes, these giants orbit each other for millions of years before colliding, emitting waves too low-pitched for LIGO to hear. But pulsar timing arrays are tuned to their frequency. If detected, they'd expose a hidden population of these cosmic titans, mapping where and how often galaxies unite across cosmic time. Yet the background might hold even darker secrets. Some theories suggest certain types of dark matter, like primordial black holes forged in the Big Bang, could also generate waves as they drift through space. Others propose cosmic strings, hypothetical defects in space-time left over from the universe's birth, might vibrate like guitar strings, adding their own notes to the hum. Each possibility twists our understanding of reality, hinting at physics beyond Einstein's equations, and the hunt is accelerating. Projects like Nanograv in North America and the European Pulsar Timing Array have already glimpsed tantalizing hints, a low-frequency signal that could be the first murmur of the background, confirming it would open a new window on the universe's structure, letting us hear the chorus of collisions that shape the cosmos. From supermassive black holes to the fabric of space itself, this hum isn't just noise, it's the universe's oldest story, told in vibrations too quiet for any one detector to hear alone. Dark matter has taunted scientists for decades, an invisible substance outweighing normal matter 5-to-1, yet refusing to interact with light or any known force except gravity. But gravitational waves might finally crack this cosmic cold case. Imagine if dark matter isn't just diffused particles but includes ancient black holes, smaller than an atom yet heavier than a mountain, forged in the chaos of the Big Bang. These hypothetical primordial black holes could lurk throughout space, bending space-time as they pass, leaving faint gravitational ripples in their wake. Here's where it gets intriguing. When two black holes merge, their gravitational waves carry precise details about their masses and orbits. But if dark matter clumps around them like an invisible halo, it could subtly distort those signals, like hearing an echo in a foggy valley versus a clear one. Some models suggest this distortion might manifest as tiny timing glitches in the wave pattern, betraying dark matter's presence. Future detectors, like the Cosmic Explorer or Einstein telescope, could spot these anomalies, turning black hole collisions into cosmic dark matter probes. Then there's the action theory, a leading dark matter candidate. These ghostly particles, if they exist, might clump into star-like objects called action stars. When these stars pass near black holes, their gravitational pull could warp space-time in unique ways, imprinting faint, telltale tremors in the waves. It's like dropping two different pebbles in a pond. One creates smooth ripples, the other leaves a slightly jagged pattern. Catching that difference would be like finding dark matter's signature in the cosmic noise. The stakes couldn't be higher. If gravitational waves revealed dark matter's nature, it would solve a mystery that's puzzled astronomers since the 1930s. We might learn whether dark matter is cold, warm, or something stranger, whether it's made of black holes, actions, or particles we've yet to imagine. Every new detection sharpens the search, turning the universe's whispers into a codebook for the invisible. And with upgrades coming, the next decade could rewrite our understanding of reality's hidden scaffolding. But the implications go deeper. If dark matter truly clusters around black holes, it could explain why some mergers appear slightly off-kilter, their spins misaligned, their orbits wobbling unpredictably. These quirks might not be random. They could be dark matter's fingerprints, subtly tugging on cosmic giants. It's like discovering an unseen hand guiding the dance of the stars. And as detectors grow more sensitive, they'll listen not just for collisions, but for the secrets whispered in the spaces between. Gravitational waves aren't just cosmic messengers. They're the universe's most precise measuring tape. Imagine trying to gauge the distance to a lighthouse in a foggy storm. Traditional astronomy relies on light, which dims, scatters, or gets absorbed by cosmic dust. But gravitational waves, they slice through galaxies unimpeded, carrying a pristine record of how far they've traveled. Scientists call this a standard siren, a term borrowed from standard candles like supernova, but with a revolutionary twist. These signals don't dim. Here's how it works. When two black holes spiral toward collision, their gravitational waves encode exact details about their masses and orbital speeds. By matching the observed wave pattern to Einstein's equations, astronomers can calculate the merger's intrinsic strength, how loud it should sound up close. Then, by comparing that to how faint the signal is when it reaches Earth, they derive the distance, just like estimating how far away thunder is by how quiet the rumble sounds. No light required, no cosmic dust in the way, just pure, unaltered space-time vibrations. This technique is already shaking up cosmology. For decades, astronomers have wrestled with the Hubble tension, a nagging discrepancy in how fast the universe is expanding. Measurements based on nearby stars and supernova clash with those from the cosmic microwave background, the afterglow of the Big Bang. The difference might seem small, but it hints at gaps in our understanding of dark energy or even unknown physics. Gravitational waves offer a third way to measure cosmic distances, independent of light-based methods. Early results from mergers like GW 170817 are already narrowing the gap, suggesting the truth might lie somewhere in between. But the implications go deeper. Standard sirens could map the universe's large-scale structure in 3D, revealing how galaxies cluster across billions of light years. Unlike traditional surveys which rely on spotting visible stars, this method works even in dark regions of space voids where matter is scarce or obscured. Future detectors like the space-based LISA mission will catch mergers from the universe's youth, tracing how expansion has accelerated over cosmic time. It's like swapping a blurry telescope for a ruler etched into the fabric of reality itself. Now, picture the extremes where this ruler bends. Near merging black holes, gravity warps space-time so severely that time slows to a crawl, light curves into impossible paths, and the very concept of distance loses meaning. These aren't just mathematical curiosities, they're laboratories for testing relativity's limits. When LIGO detected black holes spinning at nearly light speed before collision, it confirmed predictions about how such extreme rotation twists space-time like a whirlpool. Future observations might reveal even stranger effects, like echoes from quantum corrections to Einstein's theory or hints of extra dimensions hidden in the wave's fine print. What makes this so thrilling isn't just the precision, it's the audacity. For centuries, we've relied on light to chart the cosmos. Now, we're learning to measure the universe by listening to its vibrations, feeling the stretch and squeeze of space itself. Every merger isn't just a collision, it's a cosmic calibration point, a ripple that helps us redraw the map of everything. And as detectors grow more sensitive, that map will extend further back in time, closer to the Big Bang, toward answers we've only begun to imagine. One of Einstein's wildest predictions was that spinning objects don't just move through space, they drag space itself along with them, like a spoon swirling through thick syrup. Near merging black holes, this effect, called frame dragging, becomes so extreme it twists the fabric of reality into a cosmic whirlpool. Gravitational waves from these collisions carry the fingerprints of that distortion, offering scientists a front-row seat to gravity's most bizarre behavior. Take the merger GW 150914, the first black hole collision ever detected. Analysis revealed one black hole spinning at nearly half the speed of light, warping space-time around it so violently that it pulled its companion's orbit into a tilted, wobbling path. The gravitational waves recorded by LIGO weren't just a simple chirp, they were a spiraling scream of space itself being stretched and twisted. It's as if the universe handed us a recording of a black hole's spin, encoded in ripples thinner than an atom. This isn't just theoretical elegance, it's a brutal test for Einstein's theory. frame dragging near black holes pushes general relativity to its breaking point. If the waves deviated even slightly from predictions, it could hint at new physics extra dimensions, quantum gravity effects, or even exotic matter. So far, Einstein's equations have held up, but future detections of extreme spins might reveal cracks in the foundation. Imagine a black hole spinning so fast it nearly rips space-time apart. The waves from such an event could rewrite our understanding of how reality bends under pressure. And then there's the tantalizing possibility of wormholes. If frame dragging can twist space-time into a vortex, could it also twist it into a tunnel? Some theories suggest certain gravitational wave patterns might betray the presence of these cosmic shortcuts, flashes of echoes or frequency shifts, unlike anything black holes produce. While no such signal has been found yet, the mere fact that we can now listen for them is revolutionary. The universe's most extreme environments are no longer hidden. They're broadcasting their secrets in the language of ripples. What's next? As detectors grow more sensitive, they'll catch fainter, more intricate waves, ones that might reveal space-time's texture at scales we've never probed. Is it perfectly smooth, as relativity suggests, or does it have a quantum graininess? The answers could be hiding in the warped echoes of colliding black holes, waiting for us to decode them. Every merger isn't just a collision, it's a message from the edge of what's possible, written in the distortions of space itself. Wormholes have long been the stuff of science fiction, cosmic tunnels bending space-time to connect distant points in the universe. But what if they're more than just fantasy? Gravitational wave astronomy might hold the key to finding out. Unlike black holes, which leave clean, predictable ripples when they collide, a traversable wormhole merger could produce bizarre distortions in the fabric of space-time. Echoes that bounce between its throat, or sudden frequency jumps as the tunnel collapses. These signatures would stand out starkly against the smooth chirps of ordinary black hole mergers, like hearing a distorted chord in an otherwise flawless symphony. The math behind this is both tantalizing and mind-bending. Einstein's equations do allow for wormholes, but they require exotic matter, a substance with negative energy, to prop open the tunnel's walls against gravity's crushing grip. While no such matter has been found yet, gravitational waves offer a workaround. Instead of hunting for exotic particles, we could listen for the space-time tremors only a wormhole would make. Advanced detectors like the Einstein telescope or space-based LISA might spot these anomalies, distinguishing them from black holes by their unusual ring-down phase, the way the merged object settles into silence. A wormhole's final moments could produce oscillations unlike anything seen before, a cosmic fingerprint of a shortcut snapping shut. But here's the catch. Even if these signals exist, they'd be achingly faint, buried in noise. That's where artificial intelligence steps in. Machine learning algorithms are already sifting through LIGO data, trained to recognize subtle patterns human analysts might miss. Future AI could comb through gravitational wave static, flagging anomalies that defy conventional explanations. A single detection, even one with odds stacked against it, would force us to rewrite the rules of physics. Imagine confirming that the universe isn't just expanding but threaded with hidden passageways lurking just beyond our perception. The implications would ripple far beyond astronomy. Proof of wormholes would challenge our understanding of causality, quantum gravity, even the nature of reality itself. Could these tunnels stabilize long enough for matter or information to traverse them, or are they fleeting quantum flukes vanishing before anything could pass through? Every new gravitational wave detection brings us closer to answers, turning what was once pure speculation into a testable hypothesis. The universe has surprised us before. Who's to say it won't do so again? Now, consider the tools we'll need to hear these cosmic whispers. Traditional signal processing methods struggle with the sheer volume and complexity of gravitational wave data. That's why researchers are turning to neural networks AI systems that learn from thousands of simulated collisions, both ordinary and exotic. These algorithms don't just match patterns, they adapt, spotting irregularities that could hint at wormholes, cosmic strings, or other phenomena we've yet to imagine. It's like teaching a computer to recognize not just the sound of a violin, but the faintest harmonic no human ear could isolate, and the hunt isn't passive. Scientists are actively designing searches for wormhole signatures, running simulations to predict how their gravitational waves would differ from black holes. Some models suggest a wormhole merger might produce two distinct chirps, one from each mouth of the tunnel, separated by a delay as the wave echoes through the throat. Others propose frequency glitches, sudden shifts in the signal as the wormhole's geometry contorts under collision. Each possibility offers a new way to test Einstein's theory at its extremes, probing whether space-time can truly be stitched together like fabric. Of course, skepticism is healthy. Wormholes remain hypothetical, and extraordinary claims require extraordinary evidence. But that's the beauty of gravitational wave astronomy. It turns speculation into something measurable. Every strange signal, every unexplained blip in the data is a question waiting to be answered. Whether wormholes exist or not, the search itself pushes our detectors, our algorithms, and our imaginations to new frontiers. After all, the universe has already proven it's stranger than we thought. Why wouldn't it have a few more surprises up its sleeve? Now, let's talk about the unsung hero in this cosmic detective story, artificial intelligence. Without it, sifting through the ocean of gravitational wave data would be like finding a needle in a galaxy of haystacks. AI doesn't just assist, it transforms how we listen to the universe. Detecting gravitational waves isn't just about building sensitive instruments, it's about teaching machines to listen. Every second, LIGO detectors produce enough data to fill a dozen novels, a relentless stream of numbers where genuine cosmic ripples hide beneath earthquakes, passing trucks, even the vibrations of ocean waves. Finding a true signal in that chaos is like picking out a single conversation in a roaring stadium. That's where artificial intelligence steps in, not as a tool but as a cosmic interpreter, trained to recognize the faintest whispers of colliding black holes faster and more accurately than any human ever could. Take the breakthrough in 2020 when an AI named Gravity Spy spotted a black hole merger that traditional algorithms had overlooked. Buried in months of old data was the telltale chirp of two black holes spiraling together, a signal so subtle it had slipped through the cracks. The AI didn't just find it, it flagged the event with near-perfect confidence, proving machine learning could outperform decades-old detection methods. What makes this so revolutionary isn't just the speed, it's the precision. These algorithms learn from thousands of simulated collisions, refining their ability to distinguish cosmic events from glitches with uncanny accuracy. But the real magic lies in what's coming next. Future AI systems might not just detect waves, they could predict them. By analyzing the subtle tremors preceding a merger, like the way earthquake sensors detect foreshocks, machine learning models might one day alert astronomers before a collision happens. Imagine telescopes swinging into position, ready to capture the flash of a neutron star merger the moment it occurs, all because an AI heard space-time's faint prelude. And this isn't just for supercomputers. Citizen scientists worldwide are already joining the hunt through projects like Einstein at Home, where volunteers donate idle computing power to sift through gravitational wave data. Some even help train AIs by classifying detector glitches in online platforms, turning everyday users into cosmic detectives. It's a reminder that decoding the universe isn't just for experts, it's a collective effort where humans and machines work together to listen to the deepest rhythms of reality. The implications stretch far beyond astronomy. The same techniques used to find black holes are now helping seismologists predict earthquakes. Doctors diagnose diseases from medical scans. Even ecologists track endangered species by their calls. Gravitational wave AI isn't just changing how we explore space, it's reshaping how we solve problems on Earth. And as these systems grow smarter, they'll keep revealing secrets hidden in the noise, turning the static of the universe into a symphony we're only beginning to understand. Gravitational wave astronomy isn't just for scientists in lab coats, it's a frontier where anyone with curiosity can make history. Take the Gravity Spy project, where volunteers from around the world sift through LIGO data, classifying glitches that could mask real cosmic events. These citizen scientists, teachers, students, even retirees train AI by labeling interference from everything from thunderstorms to malfunctioning equipment. Their work sharpens the algorithm's ability to spot genuine signals, turning noise into knowledge. The impact is real. In 2017, a high school student combing through Gravity Spy's data stumbled on a peculiar signal. What initially looked like a detector hiccup turned out to be the faint ripple of two neutron stars colliding, a discovery that might have taken researchers months to confirm without that keen-eyed volunteer. It's a reminder that the universe doesn't discriminate. Its secrets are there for anyone patient enough to listen. This crowdsourcing revolution does more than speed up discoveries. It reshapes who gets to participate in science. Online platforms like Zooniverse and Einstein at Home let hundreds of thousands contribute idle computer time or analytical skills, passing data that would overwhelm any single team. Imagine your laptop helping to uncover a black hole merger while you sleep, or your afternoon coffee break spent tagging cosmic anomalies. Science becomes a collective endeavor, blurring the line between professional and amateur. But the real magic happens when these efforts collide with multi-messenger astronomy, the art of combining gravitational waves with other cosmic signals. Picture this: a volunteer spots a ripple, telescopes swing into action, and within hours they capture the afterglow of a neutron star collision in X-rays, radio waves, and visible light. Each perspective fills gaps the others can't, like piecing together a puzzle where every observer holds a different fragment. The challenge: coordination. Gravitational waves travel at light speed, but their alerts take precious minutes to verify and distribute. By the time telescopes respond, some fleeting phenomena, like the blue kilonova from GW 170817, might already be fading. Future upgrades aim to slash delays, automating alerts so even backyard astronomers can join the hunt in real time. What's at stake isn't just efficiency, it's inclusivity. When a neutrino detector in Antarctica or a radio telescope in Chile joins the network, they bring unique perspectives. A single event might be heard by LIGO, seen by Hubble, and felt by ice-bound sensors, each adding a layer to the story. This isn't just teamwork, it's the universe revealing itself through every possible lens at once. And the best part, the next breakthrough could come from anywhere: a classroom, a cafe, or a living room halfway across the globe. Because in this new era of astronomy, the tools aren't locked in ivory towers. They're in browsers and apps, waiting for the right pair of eyes to spot what algorithms might miss. The cosmos speaks to everyone. We're just learning how to listen together. The real power of gravitational wave astronomy lies not in listening alone, but in combining senses, like a cosmic detective piecing together clues from multiple witnesses. That neutron star collision in 2017 wasn't just a milestone because we heard it. It was the first time we saw, heard, and even felt the aftermath of the same cosmic event. Gravitational waves told us where to look, telescopes captured the fiery glow of freshly forged gold, and neutrino detectors in Antarctica caught ghostly particles from the explosion. This trifecta of data didn't just confirm theories, it rewrote them, revealing how neutron star mergers act as cosmic forges for heavy elements and proving gravitational waves travel at light speed. But why stop at 3 messengers? Imagine a future where every major cosmic event triggers a global alert system. Gravitational wave detectors flag the collision, gamma-ray satellites pinpoint the burst, radio telescopes track the aftermath, and cosmic ray sensors catch high-energy particles. Networks like the Astrophysical Multi-Messenger Observatory Network are already working toward this, stitching together instruments across continents and even in space. The goal isn't just redundancy, it's dimensionality. Each messenger carries unique information. Light reveals chemical composition, neutrinos expose the explosion's inner workings, and gravitational waves map the dance of massive objects before impact. Together, they're like witnesses describing a crime scene from different angles. One sees the weapon, another the motive, and another the escape route. The challenges, though, are staggering. Gravitational waves arrive in near real time, but light and neutrino signals can lag by seconds or even hours. Telescopes have narrow fields of view, requiring precise coordinates to catch fleeting events. That's where rapid response systems come in, algorithms that triangulate wave signals within minutes, automatically steering telescopes to the right patch of sky. The race to capture these multi-messenger events has turned astronomy into a high-stakes relay race where every second counts, and then there are the surprises. Some collisions might produce unexpected messengers, like fast radio bursts or high-energy cosmic rays. Others could defy categorization, entirely black holes swallowing neutron stars, or exotic objects we've yet to discover. The beauty of this approach is its openness to the unknown. By casting a wide net, we're not just testing existing theories, we're inviting the universe to show us what else is possible. Now shift focus to the whispers beneath the noise. While multi-messenger events grab headlines, quieter gravitational waves, those too faint or low-pitched for current detectors, might hold equally profound secrets. Future observatories will tune into these subtler frequencies, revealing a hidden layer of cosmic activity. Not every gravitational wave comes from a cataclysmic collision. Some ripple through space as gentle, persistent hums. Take white dwarf binaries, pairs of burned-out stellar cores locked in a slow, cosmic waltz. These dense remnants, each about the size of Earth but with the mass of our Sun, orbit each other for millennia, emitting gravitational waves at frequencies too low for ground-based detectors to catch. Unlike black holes that scream their mergers across the cosmos, white dwarfs whisper, a steady vibration more like a tuning fork than a thunderclap. The fate of these duos is written in their waves. Some will spiral closer over billions of years until they collide in a spectacular supernova explosion. Others might merge quietly, forming exotic hybrid stars, objects so dense they defy classification. But here's the twist: their gravitational waves act as cosmic clocks. By measuring how their orbits decay over time, scientists can reconstruct their entire evolutionary history. It's like finding an ancient tree's rings etched into space-time itself, each ripple marking another step toward their inevitable collision. Enter LISA, the Laser Interferometer Space Antenna. Slated to launch in the 2030s, this trio of spacecraft will float millions of kilometers apart, forming a gravitational wave detector so precise it could measure shifts smaller than an atom over distances wider than our solar system. Unlike LIGO, which catches brief bursts of high-frequency waves, LISA is tuned to the universe's low rumble, the domain of white dwarfs, supermassive black hole binaries, and other slow-motion dramas. What makes these quiet signals so valuable? They're cosmic storytellers. A single white dwarf binary's waves can reveal its mass, distance, and even the composition of its long-dead progenitor star. But in bulk, they become something greater, a statistical treasure trove. LISA could detect tens of thousands of these systems, mapping their distribution across the Milky Way like a gravitational census. Some might orbit so closely they complete a full revolution every few minutes, distorting space-time with predictable precision. Others could be hidden in plain sight, invisible to telescopes, but singing clearly in gravitational waves. And then there are the outliers. Certain white dwarf pairs might defy expectations, spinning faster or slower than physics predicts. These anomalies could hint at unseen forces, dark matter dragging on their orbits, or even primordial black holes flitting through our galaxy. Others might be double degenerates, pairs where one star has already exploded, leaving behind a neutron star or black hole companion. Each discovery would rewrite our understanding of stellar life cycles, showing how stars live, die, and sometimes find each other in the dark. But the real magic lies in their future. By tracking how these binaries inch closer over decades, we're essentially watching stellar fate unfold in fast forward. Some will merge in spectacular type Ia supernova, the same explosions used to measure cosmic distances. Others might collapse into neutron stars without detonating, creating ultra-dense objects that pulse with gravitational waves for eons. And a rare few could become blue lurkers, stars rejuvenated by mergers that appear mysteriously young amidst ancient stellar populations. This is gravitational wave astronomy's quiet revolution, not just listening for crashes, but for the slow, rhythmic heartbeat of the universe. White dwarf binaries remind us that space-time's ripples aren't just about violence, they're about inevitability. The patient ticking of cosmic clocks counting down to transformations we're only beginning to imagine. And as LISA tunes into their whispers, we'll gain something unprecedented. A front row seat to the universe's most delicate dances, each step recorded in the warp and weft of space itself. Now consider this: if gravitational waves from white dwarfs can reveal their past and future, could they also act as time machines? The answer might lie in the echoes of collisions that happened before humans even walked the Earth, ripples that crossed cosmic distances to reach us now, carrying stories from eras long gone. Gravitational waves are more than cosmic messengers, they're time capsules. Unlike light, which stretches and dims as the universe expands, these ripples in space-time reach us pristine, carrying undistorted echoes of collisions that happened billions of years ago. Imagine a black hole merger from the universe's infancy, back when galaxies were just assembling from primordial gas. The light from that event would be redshifted beyond recognition, stretched into invisibility by cosmic expansion. But the gravitational waves, they'd arrive with the same crisp clarity as the day they were born, a perfect snapshot of the universe's violent youth. This makes gravitational wave astronomy a form of cosmic archaeology. Future detectors, like the space-based LISA mission or the proposed Einstein telescope, could tune into frequencies from the so-called Dark Ages, the mysterious era before the first stars ignited. During this time, the universe was a silent, opaque fog of hydrogen, with no light to pierce the gloom. But gravitational waves from early black hole collisions would slice right through, offering our only window into this uncharted epoch. It's like discovering a buried civilization, not by digging up artifacts, but by hearing the echoes of their long silent drums. The potential revelations are staggering. Waves from primordial black holes, hypothetical giants formed in the chaos of the Big Bang, could reveal whether these exotic objects even exist, solving the dark matter puzzle in one stroke. Other signals might betray the formation of the first supermassive black holes, which now lurk at the hearts of galaxies. Did they grow slowly, feasting on gas and stars? Or were they born massive, collapsing directly from dense cosmic clouds? Gravitational waves from these ancient mergers would carry the answer, encoded in the subtle wobbles of their spirals. But the real test lies in pushing Einstein's theory to its limits. General relativity has passed every gravitational wave test so far, but the early universe was a realm of extreme densities and energies, conditions where quantum effects might warp space-time in ways Einstein never imagined. If future detectors catch waves from this era with unexpected glitches or echoes, it could hint at new physics, from quantum gravity to extra dimensions. The universe's oldest ripples might hold the keys to its deepest secrets. Now consider the irony. To hear these ancient whispers, we're building machines of breathtaking precision. LIGO spacecraft will measure distance changes 1,000,000 times smaller than an atom, while the Einstein telescope will bury its detectors underground to silence Earth's vibrations. These aren't just tools, they're time machines, tuning into frequencies that have been traveling since the cosmos was in its cradle. And with every upgrade, we're not just listening to the universe's past. We're rewriting the story of how it began. Einstein's theory of general relativity has withstood every test thrown at it for over a century, but gravitational waves are pushing it closer to the edge than ever before. Every ripple detected is more than just a cosmic event. It's a stress test for the laws of physics. Take something as fundamental as speed. According to relativity, gravitational waves should travel at exactly the speed of light. But what if they don't? Even a minuscule deviation, say 1 part in a quadrillion, could shake the foundations of modern physics, hinting at hidden dimensions or a flaw in Einstein's equations. LIGO observations have already put this to the test. When the neutron star merger GW170817 sent both gravitational waves and gamma rays racing toward Earth in 2017, telescopes measured their arrival times down to the millisecond. The result, they matched, confirming gravity's speed to within 1 part in 1,000,000 billion. That's like timing 2 race cars across the universe and finding they finished within a hair's width of each other. But the hunt isn't over. Future detectors like the Einstein telescope will sharpen these measurements 1,000-fold, probing for discrepancies so tiny they'd reveal cracks in relativity itself. Then there's the way black holes ring. After a collision, the merged object doesn't just go silent, it vibrates, sending out faint gravitational echoes like a bell struck by a hammer. These tones, called quasi-normal modes, encode the black hole's mass, spin, and even the shape of space-time around it. But here's the twist. If these frequencies don't match Einstein's predictions, it could mean black holes aren't quite what we think. Some theories suggest they might be fuzzballs, quantum objects with surfaces, not smooth event horizons or even portals to other universes. Each merger's ringing is a fingerprint, and so far they've all fit relativity's mold. But the next one could be the outlier that forces us to rewrite the rules. The stakes get even higher near supermassive black holes, where gravity bends space into knots. Frame dragging, the way spinning black holes twist space-time around them, should leave subtle imprints on gravitational waves. If those imprints deviate from expectations, it might mean gravity behaves differently in extreme environments, or that extra dimensions are warping reality in ways we can't yet see. Some modified gravity theories, like MUND, propose tweaks to Einstein's equations to explain dark matter without invisible particles. Gravitational waves could be the key to testing these ideas, probing regions where traditional telescopes see only darkness. What makes this search so exhilarating is its openness. Unlike lab experiments where conditions are controlled, the universe serves up collisions we can't predict: black holes spinning backward, mergers with bizarre mass ratios, or echoes that linger too long. Every anomaly is a potential clue, a whisper that the cosmos might play by rules we haven't yet imagined. And with upgrades coming, the next detection could be the one that doesn't just test relativity, it breaks it wide open. When two black holes collide, the violence doesn't end with the final merger. It reverberates. Like a bell struck by a hammer, the newly formed black hole rings, sending out gravitational waves at precise frequencies as it settles into its final shape. Scientists call this phase the ring down, and it's one of nature's most elegant experiments. These fading ripples aren't just cosmic aftershocks. They're a direct probe into the black hole's soul, revealing its mass, spin, and even the fabric of space-time around it. The math behind this is astonishingly precise. According to Einstein's theory, a black hole's ring down should produce two dominant tones: a higher-pitched ping and a deeper bong, that decay exponentially as the black hole loses energy. The frequencies and decay rates depend solely on the object's mass and spin, a property called the no-hair theorem, which suggests black holes are remarkably simple, defined by just these two numbers. But what if they're not? If future detectors catch ring-down tones that deviate from these predictions, it could mean black holes have hidden structure, perhaps quantum hair or even exotic matter lurking just beyond their event horizons. LIGO has already glimpsed hints of this ringing. In the first detected black hole merger, GW150914, scientists identified the telltale frequencies in the aftermath, matching Einstein's predictions to within a few percent. But the real test lies in the extremes. Imagine a black hole spinning so fast it nearly tears space-time apart. Its ring down might carry echoes, tiny, repeated wavelets that could betray quantum effects at the event horizon or even portals to other dimensions. Some theories, like loop quantum gravity, predict these subtle glitches, and future detectors like the Einstein telescope could be sensitive enough to spot them. Then there's the wild card. What if the ringing never stops? Certain exotic objects, like wormholes or gravistars, theoretical black hole alternatives filled with dark energy, might produce persistent gravitational wave signatures, humming long after a merger. These would stand in stark contrast to the clean decay of a classic black hole ring down. It's the difference between striking a bell and hearing it fade, or striking it and realizing it's somehow still ringing minutes later. The stakes couldn't be higher. Every ring down is a stress test for relativity, probing whether black holes truly are the perfect, featureless voids Einstein envisioned, or if they hide secrets that demand new physics. With upgrades to current detectors and next-generation observatories on the horizon, we're on the verge of listening to these cosmic vibrations with unprecedented clarity. The universe's most enigmatic objects might finally start singing in tune, or reveal a melody we never expected. And speaking of unexpected melodies, there's another mystery lurking in the cosmic chorus: black holes that don't fit the mold. Somewhere between the stellar mass black holes LIGO detects and the supermassive giants at galactic centers, there's a gap, a missing population of intermediate mass black holes, too big to form from collapsing stars, yet too small to grow into the monsters we observe today. Their gravitational waves could rewrite the story of how black holes grow and where they come from in the first place. Black holes come in two extremes: the small ones left behind by dying stars, and the supermassive beasts lurking at the centers of galaxies. But what about the middleweights? Where are the black holes that bridge this gap? the ones with masses hundreds or thousands of times that of our Sun. LIGO has spotted plenty of stellar mass mergers, and telescopes have mapped countless supermassive giants, but this cosmic middle class remains frustratingly elusive. Their absence isn't just a curiosity, it's a glaring gap in our understanding of how black holes grow from modest remnants into the monsters that shape entire galaxies. One theory suggests these intermediate black holes do exist, but they're simply harder to detect. Unlike stellar mass mergers, which produce sharp, high-frequency chirps in LIGO range, mid-sized collisions might hum at lower pitches, drowned out by Earth's own seismic noise. Alternatively, they could be loners, black holes that form in dense star clusters but rarely find partners to dance with, their gravitational waves too faint to register. There's also the possibility they're hiding in plain sight, their mergers masquerading as louder events with unusual mass ratios. Untangling these signals from the background static is like trying to hear a whisper in a windstorm. But the hunt is heating up. The next generation of detectors, like the Cosmic Explorer and Einstein telescope, will be sensitive to a broader range of frequencies, tuning into the low, rumbling mergers that current instruments miss. If these middleweights are out there, their collisions should leave distinct imprints, longer, deeper waves that roll through space like distant thunder. A single detection could revolutionize our understanding of black hole evolution, revealing whether they grow gradually by swallowing gas and stars or leapfrog in size through dramatic mergers. The stakes go beyond cataloging cosmic oddities. Intermediate black holes could be the missing link in galaxy formation. Some theories suggest they act as seeds for their supermassive cousins, anchoring the first proto-galaxies in the early universe. Others propose they're the wreckage of ancient stars far larger than any we see today, relics from a time when the cosmos burned hotter and brighter. Finding them would be like discovering a lost chapter in the universe's history, one where black holes didn't just lurk in the shadows, they built the cosmic structures we take for granted. And then there's the wild card, cosmic strings, these hypothetical cracks in space-time, thinner than an atom but stretching across galaxies, could vibrate with gravitational waves unlike anything black holes produce. Future detectors might catch their faint, high-pitched hum, a sound that would rewrite physics overnight. The universe is full of mysteries, but with every upgrade, we're tuning our ears to frequencies we once thought were silent. The middleweights may be hiding now, but they won't stay hidden forever. Cosmic strings sound like something from science fiction, threads thinner than an atom but stretching across the entire universe, left over from the fiery chaos of the Big Bang. These hypothetical flaws in space-time wouldn't just sit quietly, they'd writhe and vibrate, sending out bursts of gravitational waves unlike anything black holes or neutron stars produce. Picture a crack in ice spreading under pressure, snapping and sending tremors through the surface, except here, the ice is the fabric of reality itself. If these strings exist, their waves would be jagged, erratic, a cosmic static that stands out starkly against the smooth chirps of merging black holes. What makes cosmic strings so tantalizing isn't just their strangeness, but what they could reveal about the universe's first moments. According to some theories, they formed during a phase transition in the early cosmos, like flaws crystallizing in cooling metal, when the fundamental forces of nature split apart. Each string would be a fossil from that epoch, carrying imprints of physics we can't recreate even in particle colliders. Detecting their gravitational waves would be like unearthing a relic from a time before atoms, before light, when the universe was a seething quantum soup. The hunt for these filaments isn't just theoretical. Future detectors like LISA or the Einstein telescope could be sensitive enough to catch their high-pitched hum. Unlike black hole mergers, which fade quickly, cosmic strings might produce continuous waves, persistent, unchanging tones ringing through space for billions of years. Some models even suggest strings could form loops, vibrating at specific frequencies like guitar strings plucked by the cosmos itself. A single detection wouldn't just confirm their existence, it would offer a direct line to the universe's birth pangs, probing energies 1,000,000,000,000 times higher than anything achievable on Earth. Yet the search is a gamble. Cosmic strings might not exist at all, or they could be so rare that none lie within our observational horizon. But that's the thrill of gravitational wave astronomy. It turns speculation into testable science. Every new detector upgrade, every refined algorithm, brings us closer to answering questions that once belonged to philosophy. Are there defects woven into space-time? Does the universe still tremble from its violent birth? The waves hold the answers if we can learn to listen closely enough. And then there are the quietest ripples of all, the ones that don't come from collisions or cosmic cracks, but from the slow, patient drift of the universe itself. These whispers, almost too faint to measure, might carry the deepest secrets yet. Most gravitational wave signals come in sharp bursts, collisions that scream across the cosmos before fading into silence. But hidden beneath these violent crashes is a subtler kind of ripple, a near-constant hum emitted by spinning neutron stars with imperfections no larger than a grain of sand. These so-called continuous waves are the universe's background music, playing on an endless loop as these ultra-dense stellar corpses rotate with mind-bending precision. The challenge: these signals are maddeningly faint. Unlike black hole mergers that shake space-time with the force of a cosmic earthquake, continuous waves are more like the vibration of a single guitar string stretched across light years. Current detectors strain to pick them up against the roar of earthly noise. But if we could tune into this hum, the payoff would be revolutionary. Every tiny bump on a neutron star's surface, every microscopic mountain just millimeters tall, warps space-time as it spins, imprinting its signature on the gravitational waves it emits. Mapping these distortions would let us peer inside these exotic objects like cosmic X-rays, revealing whether their cores are made of free-floating quarks, exotic hyperon soup, or states of matter so strange they defy known physics. The hunt for these waves is like trying to hear a whisper in a hurricane. Scientists deploy ingenious tricks, like stacking years of data to amplify the signal, or using pulsar timing arrays as ultra-sensitive antennas. Some teams even search for neutron stars in binary systems, where their orbital motion creates a predictable Doppler shift, a kind of cosmic tuning fork that helps isolate the signal. The first detection would open a new window on extreme matter, showing us how particles behave under pressures so intense that atoms collapse into a sea of nuclear pasta. But the implications stretch even further. Continuous waves could act as universal lighthouses, their steady pulses allowing us to measure cosmic distances with unprecedented precision. Unlike fleeting merger signals, these persistent ripples would let us track space-time's subtle stretching over decades, probing dark energy's grip on the expanding universe. It's the difference between snapping a single photo and recording a time lapse. The longer we listen, the more the cosmos reveals. And then there's the wild card. What if some of these waves aren't from neutron stars at all? Theoretical objects like boson stars or quark nuggets could produce similar signals, their exotic physics ringing through space in frequencies we've yet to imagine. Every new detector upgrade brings us closer to catching this elusive hum, turning what was once background noise into the next frontier of discovery. The universe isn't just crashing cymbals, it's singing a slow, steady song. We're finally learning how to hear it. This quiet revolution doesn't stop at mapping stars. Those same gravitational whispers could rescue cosmology from its greatest crisis, the growing divide over how fast the universe is expanding. But that's a secret for another ripple. Astronomers are locked in a cosmic courtroom drama, and the stakes couldn't be higher. For years, two competing measurements of the universe's expansion rate, the Hubble constant, have stubbornly refused to agree. One method, using nearby supernova and Cepheid stars, suggests space is stretching at about 73 kilometers per second per megaparsec. The other, based on the cosmic microwave background, insists it's closer to 67. This isn't just academic quibbling. The gap implies something fundamental might be missing from our understanding of dark energy, gravity, or even the universe's very fabric. Enter gravitational waves, the ultimate impartial witnesses. Unlike light-based measurements, which rely on chains of assumptions about stellar brightness and cosmic dust, mergers like neutron star collisions offer a direct distance readout. Remember how standard sirens work. The gravitational wave signal encodes the merger's intrinsic strength, while the accompanying light reveals its redshift, how much the universe has stretched since the event. Compare the two, and you get a clean, assumption-free expansion rate. No calibration ladders, no cosmic dust corrections, just pure geometry written in space-time ripples. The first breakthrough came with GW 170817, the neutron star merger that lit up telescopes worldwide. Its gravitational waves placed it squarely between the feuding Hubble values, leaning slightly toward the higher supernova-based estimate. But with just one data point, the jury's still out. That's where next-generation detectors come in. Projects like the Einstein telescope and Cosmic Explorer aim to catch hundreds of mergers, mapping the expansion rate across cosmic time. Imagine tracing the universe's growth from its youth to today, watching for twists that might explain why the numbers disagree. But the real shocker: this isn't just about settling a number. If gravitational waves confirm the higher rate, it could mean dark energy evolves over time, growing stronger as the universe ages. Or worse, that Einstein's gravity equations need revision at cosmic scales. Either scenario would rewrite textbooks overnight. Alternatively, if they side with the lower value, it might expose hidden biases in our stellar measurements, forcing us to rethink how stars live and die. The clock is ticking. With each new merger detected, we're not just adding data, we're inching toward a verdict that could redefine cosmic history. Will the universe's expansion curve bend to our models, or will we have to bend our models to the universe? The waves will tell us soon enough, and when they do, the answer might not just resolve a crisis, it could reveal an entirely new chapter in the story of everything. Now consider what comes next. As detectors multiply and sensitivity sharpens, gravitational wave astronomy is poised to leap from discovery phase to routine observation, a transformation as profound as when Galileo first pointed his telescope skyward. The future isn't just about hearing more collisions, it's about weaving them into the fabric of everyday science. Right now, gravitational wave astronomy is like listening to the universe through a keyhole. We catch glimpses of collisions, but so much slips past unnoticed. That's about to change. The next generation of detectors, like the Einstein telescope and Cosmic Explorer, aren't just upgrades, they're quantum leaps. Imagine swapping a tin can telephone for a symphony hall's acoustics. The Einstein telescope, planned to burrow deep underground in Europe, will silence Earth's vibrations, while Cosmic Explorer's 40-kilometer arms, 4 times longer than LIGO, will catch whispers 10 times fainter. Together, they'll transform gravitational wave detection from rare events to routine science, spotting mergers not monthly but hourly. What does that mean in practice? Picture a cosmic traffic jam suddenly visible where we once saw only darkness. Current detectors might catch the loudest black hole collisions, but next-gen observatories will hear the murmurs of neutron stars merging in distant galaxies, the faint tremors of white dwarf binaries, even the primordial echoes of the universe's first black holes. The Einstein telescope's triangular design, with lasers bouncing between 3 underground caverns, will pinpoint sources with pinpoint accuracy, while cosmic explorers' sprawling arms will tune into lower frequencies, capturing the slow-motion dances of supermassive black holes spiraling toward collision. But the real revolution lies in the unexpected. With thousands of detections pouring in, patterns will emerge, black holes with bizarre spins, neutron stars defying density limits, perhaps even objects we've never imagined. It's like turning on a light in a forest and realizing the trees are full of creatures you never knew existed. Some theories predict intermediate black holes will finally reveal themselves. Others suggest we'll catch the gravitational ringing of exotic stars made entirely of quarks. Every anomaly will be a clue, a crack in our understanding where new physics might seep through. And then there's the dream beyond Earth. While ground-based detectors battle seismic noise, the moon offers silence. A lunar gravitational wave observatory, free from atmosphere and quakes, could hear frequencies impossible on Earth, like the universe's deepest bass notes. Imagine lasers strung between craters, measuring distortions with pristine precision. The moon's stability might even let us catch waves from the Big Bang itself, vibrations so ancient they've faded to near nothing elsewhere. It's not science fiction. NASA and ESA have already sketched proposals. The next frontier of astronomy might not be in the stars, but on our nearest celestial neighbor, listening as the cosmos thrums with secrets we've only begun to imagine. The moon has always been Earth's silent companion, but soon it could become our most powerful cosmic eavesdropper. Unlike our seismically restless planet, the moon's surface is eerily still, free from the constant rumble of oceans, weather, and human activity. That makes it the perfect stage for an ambitious new kind of observatory, the Lunar Gravitational Wave Antenna. Imagine laser beams crisscrossing between moon landers, measuring distortions in space-time with precision impossible on Earth. Without atmospheric interference or ground vibrations, this lunar lab could detect gravitational waves at frequencies so low they'd reveal mergers from the universe's infancy, events no ground-based detector could ever hear. Here's why location matters. Current observatories like LIGO are tuned to catch high-frequency waves from stellar mass black holes, but the cosmos hums with deeper notes. Supermassive black hole binaries, for instance, orbit each other for millions of years before colliding, emitting waves with periods of hours or even days, far too drawn out for Earth's noisy environment. The moon's serene surface, coupled with its lack of a magnetic field or atmosphere, lets it sense these ultra-low-frequency ripples. NASA's proposed antenna wouldn't just listen for collisions. It would map the slow-motion waltz of galactic giants, tracing how they shape the universe's largest structures over cosmic time. But the real prize lies even deeper. Some models suggest the first black holes, primordial ones forged in the Big Bang's chaos, might still drift through space, their mergers emitting waves at frequencies only a lunar detector could catch. These ancient behemoths could solve the dark matter mystery or reveal exotic physics from the universe's first moments. And then there's the background hum, the overlapping whispers of countless mergers across history. On the moon, that static wouldn't be noise, it'd be a symphony, each note a clue to how black holes grew, clustered, and seeded the galaxies we see today. Building this antenna won't be easy. Lunar landers would need to deploy seismometers sensitive enough to measure vibrations smaller than an atom, while lasers precise enough to track distortions across miles of regolith. Yet the payoff would redefine astronomy. Picture this: as Earth-based detectors catch the crashes, the Moon tunes into the murmurs, filling in the gaps of a cosmic timeline we've only begun to sketch. It's not just about better data, it's about hearing the universe in a way we never have before, on a stage where silence isn't the absence of sound, but the key to unlocking gravity's oldest secrets. Now consider what these discoveries might mean beyond equations and observatories. Gravitational wave astronomy isn't just expanding our toolkit, it's reshaping how we see our place in the cosmos. From philosophical shifts to cultural revolutions, the ripples reach further than we ever imagined. For centuries, humanity experienced the cosmos as a silent movie, a vast, luminous spectacle we could observe but never truly hear. Gravitational waves shattered that silence, revealing a universe that doesn't just glow and shimmer but thrums with vibration, humming a secret melody written in the warp and weft of space-time itself. This isn't merely another scientific tool, it's a paradigm shift, a reminder that reality speaks in more than photons, those ripples from colliding black holes. They're not just signals, they're echoes from events older than Earth itself, carrying stories that light could never tell. Imagine standing on a shore, not just seeing the ocean's surface, but hearing the whispers of every wave that ever crashed, each one a messenger from a distant storm. There's profound poetry in this cosmic listening. When LIGO caught its first gravitational wave in 2015, we weren't just detecting a black hole merger, we were eavesdropping on a tragedy written 1 billion years ago, a dance of darkness that ended long before humans walked the Earth. The universe archived that collision in space-time's fabric, preserving it until our technology matured enough to decode it. In a way, gravitational waves make astronomers time travelers, not by visiting the past but by letting the past visit us, undistorted by the eons. It's as if the cosmos kept a diary, and we've just learned to read its language. This new sensory dimension reshapes our existential perspective. Light can be obscured, blocked by dust, bent by gravity, or stretched into invisibility by cosmic expansion. But gravitational waves, they pass through everything unaltered, like a whisper slipping through walls. A supernova's light might fade or scatter across millennia, but the gravitational tremors from its collapsing core arrive pristine, carrying truths no telescope could glimpse. Suddenly, the universe feels more intimate, more alive, not a static backdrop, but a dynamic arena where even the darkest, most silent events leave resonant fingerprints. And the implications ripple beyond astrophysics. Philosophically, gravitational waves blur the line between observation and participation. When we detect these ripples, we're not just passive witnesses, we're nodes in a cosmic network, our detectors vibrating in harmony with the same space-time that connects us to colliding stars 1 billion light-years away. It's a visceral reminder that we're not separate from the universe's grand machinery, we're woven into it, our very planet flexing imperceptibly as cosmic titans clash in the void. Perhaps most stirring is how this transforms our cultural imagination. For generations, space was depicted as a silent vacuum, a visual frontier. Now, composers translate gravitational wave data into soundscapes, letting audiences hear black holes collide. Artists render these invisible ripples as swirling sculptures, giving form to the formless. Science fiction, once limited to warp drives and laser beams, now grapples with the eerie reality of space-time soundtrack. The universe isn't just a place to explore, it's a symphony to experience with movements written in gravity's own hand. This isn't just progress, it's a renaissance in how we perceive our place in the cosmos. Every new detection adds another note to the melody, another verse to the epic. And as our ears grow sharper, we'll hear not just crashes and screams, but the murmurs of neutron stars, the rustle of dark matter, maybe even the birth pangs of existence itself. The universe has been speaking all along. We're finally learning to listen. From confirming Einstein's century-old vision to chasing the echoes of hypothetical wormholes, gravitational wave astronomy has rewritten the rules of cosmic exploration. Think about that for a moment. Just a decade ago, these ripples in space-time were theoretical whispers. Now, they're a cornerstone of modern astrophysics, revealing black holes we never knew existed, neutron stars spinning like cosmic lighthouses, and perhaps even cracks in the universe's very fabric. Each detection isn't just a data point, it's a key turning the lock on a door we didn't even know was there. Take the sheer breadth of what we've uncovered. Those first chirps from colliding black holes didn't just validate relativity, they exposed a hidden population of dark giants, lurking unseen until their gravitational screams reached us. Then came the neutron-star merger that painted the sky in gold, proving these cataclysms forged the heaviest elements in the universe. And who could forget the tantalizing murmurs of supermassive black holes, slowly spiraling toward collisions that will shake galaxies? It's as if we've been handed a decoder ring for the cosmos, one that translates violence into revelation. But here's what's truly exhilarating: we're only scratching the surface. Future detectors won't just hear louder crashes, they'll tune into the universe's subtlest vibrations. The Einstein telescope could catch the faint hum of primordial black holes, relics from the Big Bang that might solve the dark matter puzzle. LIGO, soaring in space, might trace the slow-motion mergers of supermassive black holes, revealing how galaxies evolve over eons, and who's to say what else is out there. Cosmic strings vibrating like guitar strings, quantum foam frothing at space-time's edges, the birth cries of alternate universes. The more we listen, the stranger the symphony becomes. This isn't just science, it's a revolution in how we experience the cosmos. For millennia, we've been silent observers, squinting at the night sky. Now, we're participants in a grand dialogue, our detectors humming in harmony with the universe's deepest rhythms. And the best part, you're here for it. Every like, share, or comment fuels this journey, reminding us that discovery isn't just for astronomers in lab coats, it's for anyone who's ever looked up and wondered. So stay curious. The next cosmic secret might already be rippling toward us, a whisper from the dark waiting to be heard.